What is the temperature where you live today? Write in the comments the date you are watching the video, where you are. It can be a general place on the globe, and the temperature. I ask this because where I am recording today, it is currently 24 degrees Celsius. But what exactly does it really mean to say 24 degrees Celsius? What does it actually measure? For most of human history, it was literally impossible to answer this question. Not even Anders Celsius, who was the creator of the Celsius scale, could provide a convincing answer to what exactly temperature was. And this is because until the mid-19th century, temperatures were a purely empirical concept.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
All we knew about temperature was knowledge obtained through experiments, and that includes the very temperature scale we use today, degrees Celsius. Anders used two reference points to create the Celsius temperature, where water boils and where water freezes. Today we think of 100 degrees Celsius as the boiling point of water and 0 degrees Celsius as the freezing point, but in Anders's time it was the opposite. 100 degrees Celsius froze water at the coldest temperature, and 0 degrees Celsius boiled at the hottest temperature. At some point in history, we reversed this convention and started using a higher number to represent the hotter temperature. And I bring this historical curiosity to make it very clear how arbitrary our most common temperature scales are. The true physical meaning behind a temperature in degrees Celsius is simply how far or how close water is to freezing or evaporating. See? It's not complicated. At the time the scale was created, every temperature in Celsius was related to water and experiments conducted with water. But this proved to be extremely frustrating, especially as the concept of temperature gained more importance during the Industrial Revolution. Thanks to very simple experiments, we knew that if two objects at different temperatures come into contact, the hotter object cools down and the colder one heats up, and eventually both will reach the same temperature, what we call the thermal equilibrium. And we also knew that temperature, particularly high temperatures, were useful for moving things and performing work, basically creating engines. Even today, much of humanity's energy production technology is based on heating water until it evaporates, and then using the steam to turn an electric turbine. Even nuclear fusion plants, a technology we haven't mastered, use this same mechanism to transform the heat from nuclear fusion into electrical energy. And talking about heat, this was something even less understood than temperature. I am trying to make it clear that these two concepts, both temperature and heat, were very frustrating at the time, and there is a reason behind this. I want you, watching this video, to be absolutely amazed and understand the incredible magnitude of the shift in thinking when we discovered that temperature is not just something arbitrary that uses water as a reference to be defined. Or in other words, that it is possible to create an absolute temperature scale that does not depend on the properties of specific materials. Moreover, this scale has a floor, a bottom, which is indeed the lowest possible temperature, an absolute zero of temperature. This idea is powerful. It is the existence of an absolute temperature scale, of a true temperature, that shows that temperature is in fact something fundamental in nature. Temperature can be seen as an abstract concept, but it can also be studied as something fundamental, associated with the deepest laws of nature. The most famous absolute temperature scale is the Kelvin scale. The Kelvin scale is based on the Celsius scale, but unlike Celsius, where 0 is the temperature at which water freezes, the Kelvin scale sets 0 at absolute 0. And to understand how the Kelvin temperature scale began, we need to understand engines. Understanding engines is understanding the fundamentals of how energy moves in nature and how it can be used to generate work and change the world. All energy is either work or heat. And a thermodynamic engine is nothing more than an engine that transforms a flow of heat into work. There is a particularly very important type of engine called the Carnot engine. What makes the Carnot engine special is that its efficiency depends on nothing but the temperatures of the processes involved. There are Carnot engines that are electric, gas, steam, and magnetic, and their efficiency depends only on the temperatures involved, not on the material from which the engine is made. The Carnot engine generates work by moving heat from a hot place to a colder place, regardless of the exact nature of these places. And furthermore, the Carnot engine is the most efficient engine possible. No other engine can be more efficient than a Carnot engine at the same temperatures. And furthermore, there is a hypothetical scenario in which the engine's efficiency reaches 100%, where it perfectly converts heat into work. However, this case only occurs when the Carnot engine operates between some finite temperature, for example, 30 Kelvin or 300 Kelvin, and absolute zero, 0 Kelvin. In other words, if there were a magical lake at absolute zero temperature, it would be possible to use this lake to create a perfect engine, a perpetual motion machine. And that is how absolute zero was defined for the first time. It is the temperature that makes the Carnot engine 100% efficient. This is the basis of the Kelvin temperature scale, which is very useful for calculations in thermodynamics. Another thing that is very useful nowadays is the concept of atoms and molecules. This allows us to give a more intuitive definition of temperature. Temperature is, in essence, a macroscopically observable quantity that measures the energy and the motion of atoms and molecules of matter. All material in the world is made of atoms and molecules, and these atoms and molecules are not perfectly still. They are always vibrating, constantly moving and colliding with each other. Everything that moves has energy, and this is also true for the atoms and molecules that make up matter. Each individual molecule in your coffee has a particular speed and an energy associated with that speed. What temperature is measuring is how much energy is stored in the natural motion of the molecules of materials. Temperature measures the average motion of the smallest components that make up matter, such as atoms and molecules. From a microscopic point of view, temperature is a measure of average speed. This, in fact, is a perfectly good definition of temperature, but motion has a natural limit, being at rest. If all the atoms and molecules in your chair were perfectly still, absolutely perfectly static, it would be completely impossible for them to move any less. There is no less motion than being absolutely still. In other words, it would be impossible to further reduce the temperature of the chair. It would have reached absolute zero, which is the point at which it is impossible to get any colder, and also impossible to have any less motion. And this is essentially the second definition of absolute zero, the complete absence of motion. And the coolest part is that the definition of absolute zero we just arrived at using engines is equivalent to this definition that uses motion. And that is incredible, because the two ways of constructing the concept of absolute zero could not be more different. One talks about the efficiency of engines and the other talks about atoms and molecules. And this gives us the first two properties of absolute zero. At absolute zero, in theory, perfect engines are completely possible and the atoms and molecules are all perfectly still. But that's just the beginning. Absolute zero is not one of the most important concepts in physics for nothing. There is much more to be explored. So I'm going to put on one of my favorite hoodies, because we are going to slowly lower the world's temperature and see what would happen when we reach absolute zero. We will start in our normal world as a reference, at room temperature. This means a temperature of approximately 300 Kelvin, almost 27 degrees Celsius. Nothing changes. The gases in the air are still gaseous, the water is still liquid, and the walls are still solid and sturdy. The first significant change only happens when we reach 273.15 Kelvin, or 0 degrees Celsius. Here, water freezes, and this is called a phase transition. The properties of materials depend on temperature, and certain temperature variations cause drastic and abrupt changes in the properties of the material. The solidification of water into ice is a perfect example of a phase transition. But we are not going to stop here. We are going to go down until we reach 183 Kelvin, about minus 90 degrees Celsius. Now it's really cold. This is the lowest temperature ever recorded on the planet, and here some more radical changes start to happen. At this temperature, most of the chemical reactions that life uses to sustain itself no longer occur. Chemical reactions require that the involved molecules have a minimum amount of energy to happen. Various reactions increase in frequency as the temperature rises and decrease in frequency as the temperature falls. And it's partly for this reason we get a fever when we have infections. The fever raises our temperature, increasing our metabolism, the rate of chemical reactions our body performs. And this allows our body to act faster against the disease. Temperatures this low will make the chemistry that life knows impossible, especially for macroscopic life like us. At the lowest temperatures on the planet, another phase transition also begins to occur. A less obvious but very important one, which is extremely significant. Most material properties depend on the temperature, including the impact resistance of the solids. At ambient temperatures, solids are generally malleable and strong, which means it typically takes a lot of energy to create cracks in them. But at low temperatures, it is possible for solids that are perfectly strong at room temperature to become extremely brittle. And this is a type of phase transition, the transition from ductile to brittle. Materials in a brittle state are much more vulnerable, and even microscopic damage becomes a major problem. This transition has even caused an entire ship to crack in half. The ship was called Liberty, and it sailed in icy waters without having a hull made for low temperatures. The metal of the hull underwent a phase transition from ductile to brittle, and as a result, a massive crack split the ship in two. And look, we are still 180 degrees away from absolute zero. And here, even what seems solid and strong is no longer. Temperature really changes everything. So let's go even lower until we reach 77 Kelvin, about minus 196 degrees Celsius, just 77 degrees above absolute zero. This is the temperature of liquid nitrogen. Nitrogen is the main component of the atmosphere, and at this temperature it becomes a liquid. This is the temperature at which the very atmosphere of our planet becomes liquid, covering the entire surface of our planet in 12 meters of liquid nitrogen and oxygen. But we can go even lower until we reach the temperature at which helium becomes liquid, at just 4 Kelvin or minus 269.15 degrees Celsius. This is a very important temperature for modern science because it is from here that quantum effects start to become common. This temperature is so extremely low that even some macroscopic quantum effects can occur. The electrons that survive the absurd thermal contraction caused by this temperature variation become superconductors. The good news is that you wouldn't need to worry about cooling your computer. And it's not because we are just 4 degrees above absolute zero, but indeed because superconductors allow electric current to flow without resistance, which is what causes electronic equipment to heat up. Additionally, various metallic objects start to float above magnets, which is another effect of superconductors. This temperature also causes the small amount of liquid helium in the atmosphere to behave like a superfluid, flowing without any resistance and even being able to climb walls. And here we finally reach absolute zero, or about minus 273.15 degrees Celsius. At this point, all particle motion must completely stop. The main consequence of this is that the closer the temperature is to absolute zero, the easier it is to heat an object. And at absolute zero itself, even the slightest amount of heat will increase the temperature. In other words, reaching absolute zero is impossible. Even if you were to cool the planet down to that point, it would immediately move away from absolute zero. Any minimal amount of energy would be enough to raise the temperature again. Even the cosmic background radiation, which is only about 2 degrees above absolute zero, would serve as a thermal bath to warm anything at absolute zero. Even the weak magnetic interactions between the atomic nucleus and its electrons could raise the temperature from absolute zero to just above absolute zero. It is not possible to stay at absolute zero. Furthermore, it is not even possible to truly reach absolute zero. This is the third law of thermodynamics. It is impossible to cool something down to absolute zero. And here we arrive at an interesting visualization of what the lowest possible temperature is. If we stop to think about it, absolute zero is not a place we can reach just by having patience and the right equipment. It works in a way like a kind of infinitely negative temperature. You can always cool an object even further. You can reach 0.1, 0.01 Kelvin or something even lower, but you will never reach absolute zero. And that makes sense. Atoms and molecules cannot remain perfectly still, and there is even a quantum reason for this. If a particle stood perfectly still, it would be possible to accurately determine both its velocity, which would be zero, and its position. But this violates Heisenberg's uncertainty principle, which is one of the most important laws in quantum mechanics. And another interesting consequence of us never being able to reach absolute zero is that perfect engines do not exist. No engine can be more efficient than the Carnot engine, and even it is only perfectly efficient when it actually operates at absolute zero. Thermodynamics makes it clear. There is no free lunch when we talk about the conversion of energy into work. In summary, and also to answer the question from the video more clearly, nothing happens at absolute zero because it is impossible to reach absolute zero, but that doesn't mean we won't see cool things. We could see phase changes, exotic states of matter, and things we would never know existed at the temperatures we are accustomed to. I hope you enjoyed this journey to absolute zero. Thank you very much and see you next time.